Metals are malleable and ductile because of. So, if you see metals, all metals, the metallic bonding is explained by electron C model. All metal atoms lose their valence electrons and they get converted to metal ions. We know metals are highly electropositive. They lose their valence electrons and they form positively charged species, positively charged metal ion. This positively charged metal ion is called kernel. This kernel will be in a pool of electrons. These metallic kernels are arranged in a regular three-dimensional pattern in such a way that the valence electrons will be free to move and the metal ions are immersed in a sea of freely moving electrons. The kernels will be in pool of electrons and the force of attraction between the kernels and the electrons, the force which holds the metal ions and the freely moving electrons together in the crystal is nothing but metallic bond. Okay, and the strength of the metallic bond depends upon the size of the kernel and number of valence electrons. More the number of electrons, more the number of valence electrons, smaller the size and greater be the charge of kernel, stronger will be the metallic bonding. So, smaller the size and more the number of valence electrons. See, I am telling smaller the size and more number of valence electrons. If valence electrons are more, obviously the charge of the kernel will also be more. So, I am not specifying the charge of the kernel here. Size of the kernel and valence electrons. If the size of the kernel is small and the valence electrons are more, the metallic bond formed will be strong. So, the strength of the metallic bond depends on these factors. And this electron C model can be used to explain many properties of metals: malleability, ductility, lustrous nature, electrical conductivity and all. Metals are malleable and ductile. Means the metals can be made into thin sheets and can be drawn into thin wires. So what is happening? The metal can be made into thin sheets. This is malleability. And can be drawn into thin wires. This is ductility. So when mechanical force is applied on the metallic crystal, the layers of the kernels will slide on one over the other. So if the layers of the kernels slide on one over the other, the metal is deformed. Means we can convert into a thin sheet or a thin wire. Thin sheets or can be drawn into thin wires. So metals are malleable and ductile because of slipping of kernels over each other. So in electron C model, we say that metal will be, the positively charged kernel will be in a pool of electrons. Smaller the size of the kernel and more number of valence electrons means stronger will be the metallic bonding. Okay. So that is about electron C model, and why they are malleable and ductile means when force is applied on the metal crystal, the layers of metal kernel will slide over one another and so the metal can be deformed. We can make into sheets or wires. So slipping of kernels over each other is the answer there. Presence of mobile electrons means we can explain conductivity there. So first option wrong. Their non-directional nature of bond has nothing to do with malleability and ductility. High density and high melting point also has nothing to do with malleability and ductility. So malleability and ductility is because of slipping of kernels over each other.